So we're going to get started now with Chapter 7 and Section 2 now. So in Section 2, we're going to talk about estimating a population mean. It's going to look somewhat similar to Section 1, where in Section 1 we were estimating a population proportion. So it's really important to keep this notation clear between 7.1 and 7.2. So because in 7.2 we're talking about estimating a population mean, then let's cover the key concepts in 7.2. The main goal in 7.2 is to present methods for using a sample mean, or X-bar, to make an inference about the value of the corresponding population mean, or mu. You should already notice a clear distinction between 7.1 and 7.2. In 7.1, we use p hat and lowercase p. In 7.2, we're using X-bar and mu. And again, to be clear, X-bar is when we take a sample and take the mean of that sample, whereas mu represents the mean of the entire population. So again, this builds on 7.1 because we're going to take a sample, take the mean of that sample, and then use that sample mean, or X-bar, to make inferences about the entire population in which that sample came from. So the three main concepts in 7.2, we see this idea of a point estimate again, though here in 7.2, the point estimate has a meaning that the sample mean, or X-bar, is the best point estimate or single value estimate of the population mean, or mu. We're going to see this idea here of a confidence interval again in 7.2. We're going to use sample data to construct and interpret a confidence interval estimate of the true value of the population mean, or mu. So again, some of these methods are going to look similar to 7.1, but that's why it's really important to keep all this notation very clear. As we did in 7.1, we're also going to be able to calculate a sample size in 7.2. So we're going to be able to find the sample size necessary to estimate a population mean. So let's get into this. First, we're going to go through a confidence interval for estimating a population mean with a sigma that is not known. So try to remember what sigma means, and we'll go through this now. So the objective here that makes sense based on the title of this slide is we're going to construct a confidence interval used to estimate a population mean. To do this, again, we're going to take information about a sample and then use that to infer different information about our population. Here's where we see the notation now, so let's really clearly differentiate this between 7.1. So we're going to use mu as the population mean. We're going to use n as the number of sample values. That should look familiar. We're going to use X-bar to represent the sample mean. E again here is our margin of error. Then if you remember from a few chapters ago when we learned about sigma and lowercase s, where lowercase s is our sample standard deviation and sigma is the population standard deviation. So still under the same topic of using a confidence interval for estimating a population mean with a sigma, or a population standard deviation, that is not known. The requirements that we need to check for this is that number one, the sample is a simple random sample. This is an important requirement we've seen before. Number two, either or both of these conditions are satisfied. The first condition being that the population is normally distributed. The second condition being that n, or the sample size, is greater than 30. We've also touched on this previously, so determining if a population or if a sample of data is normally distributed. So we'll look at that again in 7.2. Once we've verified that these requirements hold true, then we go into setting up the confidence interval. This definition of a confidence interval should look familiar from 7.1. where the confidence interval is associated with a confidence level, such as 0.95, which in a percentage is 95%. Then we know how to find alpha from 7.1, so we take 1 minus 0.95, for example, to find the alpha value. We can do so because alpha and this confidence level are complements of one another, so they add up to 1. So again, this is from 7.1 that we've seen. For a 0.95 or 95% confidence level, we take 1 minus the non-percentage form, so 1 minus the decimal form, is equal to an alpha of 0.05. We can find an alpha value for any confidence level given as long as we convert it out of a percentage first. Within 7.2, we also have again this idea of a critical value. However, the notation is slightly different than 7.1. So the critical value t subscript alpha over 2 is the critical t value separating an area again of alpha over 2 in the right tail of the student t distribution. This very closely mirrors 7.1, but instead of dealing with a standard normal distribution and finding a z-score that corresponds to an area of alpha over 2, here in 7.2, we have a distribution that's called a student t distribution. Then within that student t distribution, we'll have an area on the right-hand side that's still alpha over 2. Then that line on the distribution that separates the rest of the area from the area of alpha over 2 is considered our critical value, but now with the notation of t subscript alpha over 2. Let's continue to talk about setting up a confidence interval now within 7.2. We again have this idea of a margin of error. However, how to calculate this is slightly different than we did in 7.1. So now our definition of the margin of error, still denoted as uppercase E, is equal to t subscript alpha over 2, or our critical value here, multiplied by s divided by the square root of n. What is lowercase s again? Well, that's our sample standard deviation. Remember that, and then sigma is our population standard deviation. Now, this new idea in 7.2 we're going to introduce is degrees of freedom, or denoted as DF. You can see here that we calculate degrees of freedom by taking the number of samples, or the sample size n, minus 1. Now, more on degrees of freedom, or DF, we calculate this as n, the number of samples, minus 1. Now, when we start to talk about how to figure out the critical value, or the t subscript alpha over 2, we'll talk about when we really use degrees of freedom here. The important part to remember is that we find the degrees of freedom by taking the number of samples minus 1. Now, again, we're still talking about a confidence interval for estimating a population mean with a population standard deviation, or sigma, that's not known. The round-off rule here is a little bit different, so there's two different scenarios for our round-off rule. Number one is when we're dealing with the original data. That is, when using an original set of data, round the confidence interval limits to 1 more decimal place than is used for the original set of data. If the original set of data, for example, had a value of 2.4, or all the values in the original data had 1 decimal point, then for rounding here, we go to 2 decimal points. That was the first way we approach the round-off rule. Now, the second way is when we're using summary statistics. So when using the summary statistics of n, x bar, and s, then we round the confidence interval limits to the same number of decimal places used for the sample mean. Remember again, n is the number of samples, x bar is our sample mean, and then s is our sample standard deviation. Let's continue talking now about key points of the student t distribution. If you're curious why we call it this, well, it was actually developed by a statistician named William Seeley Gossett. When William was ready to submit a publication about this t distribution, well, he was following his advisor's way of, instead of using their name, he was encouraged to use a pen name. So somewhat interestingly, we call it a student t distribution, but really we're not giving credit to William Seeley Gossett for developing this idea. So more on this student t distribution, if a population has a normal distribution, then this following distribution of t is equal to x bar minus mu all over s divided by the square root of n, then data that follow this formula is a student t distribution for all sample sizes n. Now we'll talk more about what formulas we'll use specifically for our practice problems. Keep in mind the key connection here. So if a population has a normal distribution, then this formula is considered a student t-distribution for all sample sizes n. A student t-distribution is commonly referred to as a t-distribution, so you'll hear it either as a student t-distribution or a t-distribution, when perhaps it should be called a Gossett distribution. So more on key points of student t-distributions or t-distributions. An important concept here in 7.2 is finding these critical values, or t subscript alpha over 2. In order to correctly find the critical value here in 7.2, we have to use this concept of degrees of freedom. Generally speaking, the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. What does this mean for us now? So in the methods used in 7.2, we will calculate the number of degrees of freedom as the sample size minus 1. In other words, we'll use this equation, degrees of freedom, or df, is equal to n minus 1. And again, keep in mind we need to apply this degrees of freedom in order to find our critical value here within this realm of student t-distributions. For a little bit more context on this idea of degrees of freedom, let's say we're given a set of numbers like 4, 9, 8, 10, and 7. If we determine the mean of these values, we get a number of 7.6. To calculate the number of degrees of freedom for this set of data, we'd count these up, 1, 2, 3, 4, 5 data points. Then we take n minus 1, or 5 minus 1 is equal to 4. So for this particular set of data, our degrees of freedom, or df, is equal to 4. The important takeaway is knowing that degrees of freedom, we calculate that as n minus 1. If you're interested in another way to think about this, then we can say that if we know the mean, in this case 7.6, then we only need to know 4 of the other values to then determine the one other value, or the fifth value. In other words, we needed to know the mean and then n minus 1 data points. We didn't need to know all 5 data points for this case. Again, the key takeaway for us is to find the total number of samples, then minus 1 for our degrees of freedom. So we need to know the degrees of freedom in order to calculate or find our critical value, or t subscript alpha over 2. So if the set of data does fit a t-distribution from that equation we saw on slide 10, then instead of finding the z subscript alpha over 2, we're going to find the t subscript alpha over 2. To find this critical value, we can use Excel. I'll show you how to do that. We can also use now table A3. Another plug for Excel here is that Excel, or any other form of technology that does statistical analysis, it can be used for any number of degrees of freedom. However, if you're going to use table A3, we can only use table A3 for a select number of degrees of freedom only. So a recommendation I put down here is to consider using Excel for this style of question. I'll show you how to use table A3 as well, though. So if we're going to use table A3 to find this critical value of t subscript alpha over 2, but let's say the table doesn't include the exact number of degrees of freedom that we're interested in, we have 2 options here. We could use the closest value, or we could be conservative by using the next lower number of degrees of freedom. If you go and look at table A3, which we'll practice using a little later in 7.2 lecture, then you can find all the degrees of freedom that are listed. But again, when you use Excel, you don't have to worry about that. You can use any number of degrees of freedom. In other words, we can have a sample size of any amount, right? Because we find the degrees of freedom by taking n, the sample size, minus 1. Now, if you're wondering what's the difference between the normal distribution and using this t-distribution, well, the student t-distribution is different for different sample sizes. For example, look at distributions of n equal to 3 and n equal to 12. So here in green is our standard normal distribution. We have a mean of 0. We have a standard deviation of 1. For standard normal distributions, we didn't talk as much about the sample size, but here for student t-distributions, we can differentiate between n equal to 12 and n equal to 3. So as you can see, the student t-distribution has the same general shape, so it's symmetric, it looks bell-shaped. So it has the same general shape as the standard normal distributions we're used to working with. But it has a greater variability that is expected with smaller sample sizes. Even a sample size difference of 9 here, so n equal to 3 is in blue, you can see that distribution there. N equal to 12 is in a kind of maroon color, you can see the distribution there. So you can see as the smaller the sample size is, then we have a greater variability in that distribution shape. How can we say that? Well, we know that each of our values sort of fills in this distribution. The wider the spread is of our distribution, the more varied our samples are. If all of our data was very close to one another, then we'd have a really nice, sharp distribution that's pretty thin. So you can see that n equal to 3 leads to somewhat of a wider distribution than n equal to 12. And n equal to 12 is still a slightly wider distribution than our standard normal distribution. So to summarize, even seemingly small differences in sample size lead to different shapes of these t-distributions. So more on this difference between standard normal distributions and our t-distributions is that student t-distributions, again, have that same general shape. So they're symmetric, they're bell-shaped, as are the standard normal distributions, but student t-distributions have more variability when we have small sample sizes like this. More variability in a distribution leads to a wider distribution. Now, one commonality between the student t-distributions and a standard normal distribution is that student t-distributions have a mean of t equal to 0, just as we saw for standard normal distributions that have a mean of z equal to 0. So student t-distributions, a t equal to 0, standard normal distributions, a z equal to 0. A difference here, though, between standard normal distributions and these student t-distributions is now talking about the standard deviation. Remember, for standard normal distributions, we have a mean of 0 and a standard deviation of 1. Now, for student t-distributions, we have a mean of t equal to 0, but our standard deviation varies. More specifically, the standard deviation of t-distributions vary with the sample size. The standard deviations of student t-distributions are greater than 1. The standard deviations then are greater than what we see for a standard normal distribution. Okay, so far we've seen some commonalities here, right? So t equal to 0, z equal to 0. But for student t-distributions, the standard deviation is greater than 1 because we're working with smaller sample sizes. Now, with student t-distributions, though, as the sample size, or n, gets larger, then our student t-distribution gets closer to a standard normal distribution. What would that mean for the standard deviation then? So as sample size gets larger for a student t-distribution, then that standard deviation value would get closer to 1, because it would more closely then start to resemble a standard normal distribution. Okay, so that was a lot of background information. Now let's start to apply what we know and start to work problems and look at examples. So first, let's cover the procedure for constructing a confidence interval for mu. How else can we read this? This is the procedure for constructing a confidence interval for the population mean, or mu. Step number 1, verify that our two requirements are satisfied. That is that the sample is a simple random sample and the population is normally distributed, or our sample size n is greater than 30. Step number 2, when sigma, or the population standard deviation, is unknown, which usually it is unknown, Then we use n, the sample size, minus 1 to find the degrees of freedom, and we can use technology like Excel or table A3 then to find our t subscript alpha over 2, which is our critical value. Just like we saw in 7.1, this critical value corresponds to a desired confidence level. If you recall in 7.1, when we knew our confidence level, that we could find our alpha value, we took alpha over 2. That gave us the area on the right-hand side. Then we took 1, the total area under the curve, minus alpha over 2. Then we found the corresponding z-score, right? We found that critical z alpha over 2. Here now, we'll use Excel or table A3 to find our t subscript alpha over 2. Also importantly, we need to factor in the degrees of freedom by taking the sample size n minus 1. Then again, similarly to 7.1, but with a different formula, we're going to evaluate the margin of error, or E. To find the margin of error E for a t distribution, we're going to take t subscript alpha over 2, or the critical value here, multiplied by s over the square root of n. What is s again? That's our sample standard deviation, and then sigma is our population standard deviation. Step number 4, use the value of the calculated margin of error, or E, and our sample mean, or X bar, and substitute the values in one of the formats for confidence interval. This should sound familiar to 7.1 again because we took P hat plus E and P hat minus E. Here in 7.2 so far, we're going to take X bar minus E and X bar plus E. Remember that X bar is our sample mean. It can also be considered a point estimate here. Then we find X bar minus E, we plug in that value there, then we still have mu, our population mean, in the middle. Then on this side, we'd substitute in the value for X bar plus E. These formats are saying the same thing, so X bar plus and minus E. Here, X bar minus E and X bar plus E. Again, remember we're building up to constructing a confidence interval to estimate the population mean, or mu. Then step number 5 is how we round off. Remember there's 2 different scenarios here. So if we have an original set of data values, we round the confidence interval limits to 1 more decimal place than used for the original set of data. If, however, we're using summary statistics of n, X bar, and s, then we round the confidence interval limits to the same number of decimal places used for the sample mean, or X bar. Okay, with that background and with those procedural steps, let's try this example of finding a critical value t alpha over 2, which corresponds to a 95% confidence level, given that the sample size has n equal to 15. Let's start working through the solution now. So one thing we can do first is to know that n is equal to 15, our sample size is equal to 15. To find the degrees of freedom, we take n minus 1, or 15 minus 1, that's equal to 14. Now we needed to calculate this degrees of freedom in order to find our critical value of t subscript alpha over 2. Similar to 7.1, we also need to use this information of a 95% confidence level. When we take 95%, take it out of a percentage, that's 0.95. Then we know that our confidence level of 0.95 and our alpha value are complements of one another. So we take 1 minus 0.95, we get an alpha value of 0.05. Still somewhat following along the lines of what we did in 7.1, then we can take alpha divided by 2. So 0.05 divided by 2, that's 0.025. The meaning of alpha over 2 are these 2 tails of now the t distribution. Now let's acclimate first to what we see here before going forward. So we have this distribution, it looks bell-shaped, it looks symmetric. In the middle of this t distribution, we have t equal to 0. We just found this value here based on this 95% confidence level. So we found that the area here is 0.025. It's on this tail of the t-distribution. On this right tail of the t-distribution, we also have that same area value of 0.025. Now, again, I mentioned we can use Excel or Table A3 now. So let's first go through doing this with Excel. Now, we already solved for the degrees of freedom. We also already solved for our alpha value. Let me show you how I set this up in Excel as well. So if I have my confidence level in a percentage of 95%, I can find the confidence level in a decimal form by taking 95 divided by 100. We get 0.95 for that. Then we take 1 minus 0.95 to get my alpha value. That's equivalent to 0.05. Now, importantly here for 7.2, I know my sample size of n is equal to 15. But what I also need to know to find this critical value is to take 15 minus 1. I have to find the degrees of freedom. That's equal to 14. Now, we have a t-distribution, and we know the area here on this right-hand tail. The critical value for a t-distribution, we call that t alpha over 2. That's really the same concept of finding the z-score, but now we're working in a t-distribution. So now what we need to do is find this equivalent t-value that corresponds to this point here, where the area to the right is 0.025. Now let's go through this new equation using Excel. So to find this t alpha over 2, the critical value for a t-distribution, we're going to use this equation. We type in equal sign to set up a function, t.inv.t2, then an open parenthesis. We only need 2 values here to get this critical value for a t-distribution. It's important here because these aren't labeled maybe exactly what you think they'd be labeled. Instead, they're labeled a probability, comma, degrees of freedom. The probability value that goes in here is our alpha value. I'll say that again. The probability value that goes into this part of the function is our alpha value, not alpha over 2, not 1 minus alpha. We put in alpha here for our probability for this style of function. So again, equal sign t.inv.t2, open parentheses, my alpha value, comma, my degrees of freedom. When I click enter, then I should get this answer now. So I say the critical value, or t alpha over 2, is equivalent to 2.145. It can also be denoted like this, t, which alpha over 2 is 0.05 divided by 2, that's 0.025. So we could also see it written like this, or t subscript 0.025. Okay, so practice this along with me. Make sure we find the critical value and t alpha over 2 as 2.145. Star in your notes that we use an alpha value here as our probability value. Then we also find the degrees of freedom. We use that here in this equation. Now, given our degrees of freedom is equal to 14, let's also practice using table A3. So table A3 can be found in your book. It's also available in the ebook version. So here on this table, on the left-hand side, we have our degrees of freedom. And then up here, we have area in 1 tail and area in 2 tails. What you'll notice is that area in 2 tails is double the area in 1 tail. So essentially, area in 2 tails here versus area in 1 tail, they're connected. So make sure you're looking at the correct place in table A3. So for our scenario here, to find the critical value using table A3, we're going to go to the column of 0.05 for the area in 2 tails. This would be the same as us looking in the column of 0.025 for the area in 1 tail. So now again, we're here in table A3. Then we need to look at our corresponding degrees of freedom, and then we can find our critical value this way. Using table A3, we get the same thing as we would using Excel, so 2.145. The caveat to table A3 is if we have a degrees of freedom that isn't listed in the table. But if you do choose to use table A3 and your degrees of freedom is not listed, there are some workarounds for that. You could look at the closest degrees of freedom that's listed in the table, or go a little bit below your degrees of freedom to be conservative. So, using table A3, the number of degrees of freedom, we have n minus 1 or 15 minus 1, that's 14. We need that value when we're using table A3. We also use the fact that it's a 0.95 confidence level because then we found our alpha value this way. Putting this all together, we get a t subscript alpha over 2 or t subscript 0.025 because that is alpha over 2 of 2.145. And again, just keep in mind if you're using area in one tail or area in two tails, and be sure you're clear on the distinction here. You can use either variation, just make sure you're looking in the correct column when using table A3.